So we moved on to part C of our potential energy graph question. And part C asks, how would you calculate the velocity needed to no longer be in orbit? And it says, calculate this value for Earth. So now in this part, we are just given this last graph, the graph where our total energy was positive. Because in part B, we were focusing on the graph where our total energy was negative, and that meant that we were bound to Earth in an orbit. But now in part C, we no longer want to be in orbit, and this means that we are evaluating a graph that is telling us we are unbound to Earth, that we no longer want to be in Earth's bounds. So we need to calculate the velocity needed to no longer be in orbit. So how are we going to do that? Well, instead of evaluating forces, because last time we evaluated uniform circular motion equal to Newtonian gravitational force, now we want to evaluate energy, because we want to be having enough kinetic energy needed in order to counteract the gravitational potential energy that is trying to pull us back toward Earth. So of course, if we just write out these two values as their equations, kinetic energy is 1/2 mass times velocity squared is going to equal our big G constant times the mass of Earth times the mass of our object divided by the radius of Earth rather than the distance from Earth. So when we solve for this velocity here, the escape velocity for any planet will be based on that planet's radius. So now we just have to set everything equal to this velocity here. So the first thing we do is we multiply by 2 on both sides. So mass times velocity squared is equal to 2 times big G times the mass of Earth times the mass of our object divided by the radius of Earth. So then we divide by the mass of our object, and that cancels out. Our velocity that we want squared is now equal to 2 times the big G constant times the mass of Earth divided by the radius of Earth. And of course, all we have to do is square root on both sides, and we're going to do the same thing as last time by just erasing that squared, because we know we're gonna square root on both sides. And so that means that our escape velocity is going to equal the square root of 2 times our big G constant times the mass of Earth divided by the radius of Earth. So the last thing we need to do then is we need to calculate the escape velocity for Earth. And we will need the mass of the Earth and the radius of Earth. And I have these on a separate piece of paper next to me, so I'll just write these down. The mass of Earth is equal to 5.972 times 10 to the 24th kilograms, and the radius of Earth is equal to 6.371 times 10 to the 6th meters. And we know our big G constant, hopefully, so we can just plug these values in. Our escape velocity for Earth is equal to the square root of 2 times 6.67 times 10 to the negative 11th times the mass of Earth, which we can just put in our calculator separately. and then divided by the radius of Earth, because those are long numbers and we want to save time. So we are just going to calculate this real quick, and we get that our escape velocity to escape the Earth's orbit is 1.12 times 10 to the fifth meters per second. So no matter what object you have, it needs to be moving at this velocity in order to no longer be in Earth's orbit. And of course, as we said before, this changes based on the planet that you're on, because then you'll need to plug in its mass and its radius in order to solve for its escape velocity. But otherwise, that concludes part C and our problem.